Hi, we are going to discuss TrueLearn paper which was published in AAAI this year. So this paper pretty much proposes a family of algorithms that uses Bayesian reasoning to match lifelong learners to open educational resources. In our case, we are using a video viewing platform where users are watching video lectures, and based on the topical content of this material of these videos, we want to predict if they are going to engage with the next fragment of the video or otherwise. So today's presentation, we are going to have this structure. So we are going to start with the background of the work, and then we are going to go to the, just to give a bit of context, and then we are going to look at the related work that led to the algorithm, and then to go a bit into how the algorithm works, and then the conclusions that we derived. So this work has been done as part of the X5 Gone project. So the whole point of the project is to discover open educational resources that are distributed or scattered around the internet, and to put them in one place so that we can understand them and then match them to the right learners at the right time. So how we want to do this in this project is by using artificial intelligence, as you could guess. So before going into detail, one might wonder what an open educational resource is. So according to the Hewlett Foundation's definition, an open educational resource is a learning material. So there are a few important things. It could be of any medium. It could be a PDF, it could be an exercise, it could be a video, and then it has to be openly licensed, which means it has to provide no cost access, use, adaptation, and redistribution. So in a nutshell, what this is a teacher would create an educational resource and distribute it with a license that has no restrictions for another person to use it, or even to repurpose it and create another version of that learning resource. So this is pretty much like the open source for educational materials. And so this is the background context of where the project comes from, and using this, what we wanted to do was to build a recommendation algorithm that we can use with the open educational resources that we index. So I'll start with the related work relating to the TrueLearn paper. So one of the interesting things that we noticed is that in our dataset, the dataset that we had access to, we had information about how users watch videos, and we wanted to see if we can predict user engagement, because if we want to match educational resources to learners, what we want is to provide learners with educational resources that they will engage, because that is the first step for learning from these materials. So in the literature, there has been a lot of reporting about how educational resources are rapidly being produced lately, and there have been reports that demand for detecting quality or managing quality at scale of these rapidly produced educational resources. And then the problem with this is, if we wanted to provide the educational resource that is relevant to a learner, we need to understand, we need to match these learners with these materials, which is kind of analogous to how a conventional recommendation system works, where you match an item to a user. But educational recommendation systems, as it turns out, need to satisfy additional requirements. For example, it needs to incorporate novelty of educational materials, which means you have to learn something new over time. And then it also, when you want to learn something new, you can't just learn things randomly that are unfamiliar to you. There has to be sensible learning trajectories that have to be incorporated. So these are some of the additional features that we identified to be required of educational recommendation system. And at the same time, as much as it incorporates novelty and what the person already knows, it also has to align with users' interests, so their learning goals for that matter. So by looking at these different findings, we formulated that a model that would drive the learner's engagement with an educational resource. And here what we identified was 4 different factors. One of them is the quality of the educational resource, and then how much background knowledge the learner has already within them, and based on that, how much the degree of novelty that a given potential educational resource would introduce to the learner, and finally the interests of the learner that will spark curiosity within the learner. And what we hypothesize is that there are these 4 factors that together will drive the person's motivation to engage with an educational resource. Before complaining about educational additional features that are required of educational recommender, we should look at what type of educational recommendation systems already exist. So I already said that contrast to a traditional content recommender, these educational recommenders require additional features, some of which I discussed earlier: novelty, learning trajectories, etc. And currently there are, this doesn't mean that currently people don't have educational recommendation systems. So they use systems that are that come from collaborative filtering approaches. Here the problem is they don't really understand the content. People mainly use the interactions between the learning resources and the and the users, but they don't really account for what is being taught, what information is included inside the learning resource. On the contrary, you have the content-based approaches. The problem here is mainly you get into this similarity-based recommendation approach, where after a while you get rabbit holed into a very niche topic, because it keeps giving you new different materials with the same topical contents, which is not that stimulating or encouraging in terms of educational objective. And then there are hybrid approaches where they try to sort of incorporate things like trajectories, but the problem here is usually when you want to incorporate something like a trajectory, people use manually defined trajectories, and this works because it is accurate, but at the same time these type of approaches are not scalable, they are not domain agnostic, they are very specialized to, let's say, physics or computer science, where experts spend time producing these trajectories. So this leaves a gap for making a recommendation system for education which addresses these issues, and that is kind of the motivation behind this work. And we also identified other features that are desired of a educational recommender. So one of those things is the cross modality and cross linguality. Some students might come from different backgrounds, might be bilingual for that matter, or trilingual. And one of the things that Lane argues is that a high quality educational resource is something that picks the right media to enable the learner to achieve their learning goals. What that means is to be able to find the material across multiple languages, multiple modalities such as PDFs, videos, is useful in educational recommender system. Transparency in educational recommender systems has added value, where the learners can reflect on the system's understanding of their knowledge state, for example, and that would trigger things like metacognition processes such as reflection, motivation. It also encourages the learner to collaborate with the system to sort of have a joint objective to learn with the system. Then data efficiency is a very important aspect, where in an educational recommendation system you can't bombard the user with questions explicitly asking, do you know this, do you know that, would you like to take a test on this topic, for the system to verify if the person knows this. So we have to be data efficient, try to rely on implicit feedback as much as we can, which is also a trending phenomenon in recommendation systems in general recently. And we also spoke about novelty and interests. Then eventually, if we are going to use this with lifelong learning scenarios where a huge population of users are going to have free form type of learning trajectories, it has to be scalable. So these are some of the other features that we kept in mind when we designed the algorithm. And then we can't also ignore the the plethora of work that is regarding personalized learning systems. So these do not necessarily mean recommendation systems, but intelligent tutoring systems are AI powered systems that would allow a person to learn. So usually these systems are good at providing question sets to learners in such a way that they can verify if a person is mastering a particular skill and then move on to a different skill. So when we look at in a nutshell personalized learning systems, the community identifies multiple uh, different components that have to be there. So there's the domain model, which is to do with the knowledge domain. So it might be science, computer science. So this is mainly to do with the trajectory. Then there's a tutoring model where you have to account for the different pedagogical approaches. So one of those approaches, for example, is what is called the flow state, where it has been shown that when you are teaching a person, you need to introduce them novel information, but this novel information should not be too easy nor too hard for the learner. So you need to keep them in a state of flow. And then there is the student model, where you try to identify the learner's state, which is to do with the knowledge of the learner, the emotional state of the learner, the affective state, their goals, and etc. So we need to take these learnings into account as well, from which we thought we want to incorporate these pedagogical approaches when we think about novelty, for example, and also the student model, where we try to identify the learner's state in terms of knowledge in this stage. So when we think about educational systems, personalized educational systems, there are two main components. One of them is called content analytics, where you try to identify how to represent the educational resources. So here currently the problem is that most of the most reliable methods are handcrafted methods, where domain experts identify what they call knowledge components. So knowledge components are atomic units of knowledge that can be learned and mastered. So a maths expert would look at a bunch of learning materials about mathematics and say, oh, this particular resource has the knowledge component, let's say multiplication. Then the other one would have area of a shape. So this type of knowledge components are manually identified. As you would imagine, this is very expensive. It takes a lot of domain time and effort, and it also represents the view of that subject in the eyes of a very handful of experts. So there are problems with this method. So in in relation to that, people have proposed automatic methods. Mainly they are either unsupervised methods or neural deep learning methods. So both of them have their own challenges. Unsupervised methods, usually if you think about LDA or clustering approach, the hyperparameter tuning is very complex. Therefore the stability of these solutions are quite challenging. And when we look at the deep learning methods, although they are very superior in terms of performance, there are problems relating to interpreting what the model represents, what knowledge does the encoding represent, and so on and so forth. So here there is an opportunity, and there's been a new trend of using something in the middle. One of these methods is entity linking, where you try to take a free form text and try to associate that text with Wikipedia concepts. So this way you can automatize figuring out what topics or what knowledge components are included in an educational resource. At the same time, you work with an ontology that is humanly intuitive and which is easier to express or explain to a human. So these are like the different approaches that are available for content analytics. And then the other part of educational systems is learning analytics, where we focus on the learner state. So learner state is, as I said earlier, to do with the knowledge state, the interests or the goals of the learner, the affective state, and etc. So in terms of knowledge state, which we have been focusing on in the TrueLearn work, there are two main schools of approaches that are being used. One is to use the item response theory, the other is to use what is called knowledge tracing, which is a Bayesian interpretation of how a person learns. And then there's novelty and interests that are also used for learning analytics, but they are usually used as they are, in the sense interests, as you have a representation of interests of the learner and you use that alone to make a recommendation system, for example. So I'm going to quickly elaborate on the two different learning analytics approaches. So item response theory is a method that is very old, as you can see, came from like 1960s from psychology. So it comes from trying to test a person with a document and try to model the person's skill and the document's difficulty at the same time. So here the hypothesis is that if the person has enough skill, which is the latent trait in this figure, good enough for, like, if the latent trait or the skill of the learner matches up to the degree of the difficulty of the item that the person is interacting with, they are more probable to succeed. So this is mainly developed in the context of answering tests. So that's why the figure says probability of success, because here it's about the person's skill relating to the difficulty of a question gives you the probability of successfully answering the question. So this has evolved over time, where this algorithm has then been used to measure people's skill. It's mainly used, it's popularly used in chess, where you have this ELO algorithm, which is a version of item response theory. So there the objective is, a person has a latent skill. If the person is when that person plays games with other players who also have this skill estimation, we can, based on the outcomes of these games, you can update the latent skill level of these people. So this has been used by Microsoft Research to build the true skill algorithm, which is the algorithm that is being used in Halo multiplayer game, where they use the outcomes of people's performance in games to model the skill of the person, and based on that they can identify which teams would create more interesting games, which means, teams that have similar skills, if they play against each other, will lead to more exciting games for the learners compared to putting a bunch of very skilled people with very new non-skilled gamers to play in a game where it would be intimidating to one group and too boring to the other group. So this is one approach where people use to assess the skills. And the knowledge tracing method is a Bayesian method where you sort of model the person's skill as a hidden Markov model, where you observe how people answer to questions, and then there's a latent binary variable, which is the probability of the person knowing this or mastered this skill or otherwise. And based on the outcomes you get for the questions you answer, you try to recover the skill state of the learner. So this is the other approach which is popularly being used in intelligent tutoring systems. So what we did was to actually use the item response theory to which also allows us to incorporate novelty in some sense to create the TrueLearn algorithm, which brings us to the actual work in the paper. So this is the the first engagement model that we identified, and out of that the green highlighted part is what TrueLearn represents. So TrueLearn tries to use the engagement of users with video lectures to recover the current knowledge and also model the novelty of that content or educational resource brings to the learner using a Bayesian method. So here it's as I mentioned earlier, TrueLearn is a family of Bayesian algorithms inspired by TrueSkill algorithm. So in TrueSkill, what happens is you have multiple players playing Halo, playing against another team of players, and when one team wins, we can update the skill parameters of both the winning team and the losing team. So here, instead of two players or two teams playing against each other, what we did was we modeled a person interacting with a video lecture as a game that is being played between a learner and an educational resource. So the learner has a team of skills that is required to interact with this educational material, and the educational material has multiple topics to different degrees of difficulty. So what we are trying to do is, by observing the topics in the educational resource, can we recover the skill of the learners based on the interactions that they have. So here we are working where we use entity linking to annotate the educational resources with the topics, which means we are working in the Wikipedia topic space, which is a humanly intuitive learner representation that could be interpreted and also scrutinized to one degree. So this algorithm tries to infer the learner's knowledge state, and it also incorporates novelty, as you would see in the next slide. And then eventually that knowledge representation is used to predict if the person is going to engage with a video lecture. Here what we define as engagement is, if we take a 5-minute part of a lecture, is the learner going to consume at least 75% of that video piece. And this work was also recognized as a innovation, recognized innovation at UNESCO Mobile Learning Week a few months ago. Exciting times. So now I'm going to get into the hypotheses that are behind the TrueLearn algorithm. So here there are 4 diagrams, of which the 2 rightmost diagrams are to do with TrueLearn, but the 4 diagrams sort of explain how we transition from the assumptions in intelligent tutoring systems to TrueLearn. So in the beginning, in intelligent tutoring systems, when people use item response theory or knowledge tracing, we deal with questions, and questions have difficulty, as you can see from the x-axis in the first leftmost diagram. And then you have the learner skill, and you have this diagonal where the difficulty of the question equals to the learner's skill. And what happens is, in a nutshell, if the learner has less skill than the difficulty of the question, the person is going to get the incorrect answer. Otherwise, if the learner has more skill, they're going to get a correct answer. So from here, we transform into the second diagram, where we go from question answering to engagement. So here what happens is, the learner has a particular set of skills that will allow the person to understand the video. So if the learner has more skill than the depth of knowledge that the video demands, the person can engage. Therefore, it's a successfully engaged instance. Otherwise, they are not going to engage. So the problem here is, here we assume that the knowledge state of the learner is the only factor that matters when it comes to engaging with a video. But when you read other people's work, you see that there are a zillion factors, including time constraints, that will make this side, where the engaging side, although the learner has more skill, they might engage or they might not engage. So here the problem is that all the two diagrams in the middle, although they represent sensible scenarios, there is no novelty here. Here what it says is, in the best case scenario, the learner still needs to have more knowledge than what the video provides for them to engage. Whereas in the fourth scenario, which is the TrueLearn novelty algorithm that we propose, we have this hypothesis where you have the diagonal where the resource depth of the material equals to the learner's skill. So here what we hypothesize is, there is this sweet spot in the middle, which is like a margin, which goes on both the sides of the diagonal, where the person is going to engage, which means in one side, if the learner has more skill than the resource depth, then the person is trying to consolidate what they already know. Whereas if you're on the other side of the buffer, you are trying to learn something new. At the same time, if the material is too difficult, if the resource depth is far too much in comparison to the skill the person has, it's going to be difficult, therefore the learner is going to disengage. Similarly, if the material is extremely easy, the learner is going to get bored and then disengage with the video, because it's a waste of time to watch a 20-minute video if you are already super clear and strong about what is being spoken in the video. So we make this hypothesis in TrueLearn novelty to incorporate novelty into the algorithm. So now we go to the experiment bits. So when we looked at this model, we couldn't really find any any recommendation algorithm in education space that uses topics and try to model learners to predict engagement. Therefore, we came up with a range of different baselines. So some of the naive baselines we used was persistence and majority model. So the persistence model, what it does is, your next label will be your previous outcome. So if you engaged in this time step, your next prediction would be the person is going to get engaged. If you disengage in the current time point, the prediction would be the person is going to disengage. Then we have the majority model, where what we do is, at any given time point, we use the majority label from their past to as the prediction for the next time point. So here what we are trying to do is, we have individual learners who are watching videos. What we are trying to do is to at any given time point, we want to consider the data that we already see as the system and predict if they are going to engage with the next video that they are going to watch. So alternatively, we also built online knowledge tracing model. So the knowledge tracing model in the intelligent tutoring systems literature is an offline one-off trained model, whereas we created the online version of that based on Chris Bishop's new machine learning book. And then we also use TrueSkill as it is to model the difficulty of the video and the skill of the learners at the same time. Then we created three different models. One of them, we still try to model the difficulty of the video, but instead of the video being the object, we try to model the topic of that is consistent in the video. Then we use this fixed depth and TrueLearn novelty models, where we assume that we observe the difficulty. So these are the factor graphs for the 4 models. So here first you see the knowledge tracing model where you have a Bernoulli variable. This is the Markov network, hidden Markov model that I was talking about, where you have a latent skill and you eventually observe the output, and based on that you try to learn the skill factor. Then there's the vanilla true skill where you have for each person there is a skill, and then for each video there is a difficulty value, which are both latent, and then based on the outcomes you learn the two parameters which are both Gaussians in this case, as you can see. So then we have TrueLearn dynamic depth. Instead of having one Gaussian for the learner and one Gaussian for the material, we have multiple Gaussians which represent the different Wikipedia topics the learner is acquiring skills in, and at the same time the different Wikipedia topics where the educational material has topical content in. And based on that we try to learn multiple Gaussians here. And in the TrueLearn fixed depth model and the novelty model, we assume that we see the degree of depth or difficulty of the topics in the material. How we do that is we have the Wikipedia topics that are associated with the document, uh, generated via entity linking. Then we calculate the cosine similarity of the TF-IDF vectors between the educational material, which is the video transcript in this case, and the Wikipedia page of the concept, and we treat that as a proxy for the depth of coverage of that topic in this document. So here you can see that here it's a colored variable, which means this is an observed variable, and then based on these observations we are trying to learn these skill parameters for the topics of the learner, which is also in the Wikipedia space. And here we have the fixed depth and the novelty both represented in this diagram. So the difference is in the fixed depth we assume this third diagram, where we assume that if the person has to have more skill than the difficulty or the resource depth to engage. And on the novelty we have this hypothesis where there is the sweet spot, which is determined by the final factor, where the binarization of the probability value depends on here the skill being greater, so the difference between the skill and the resource depth being greater than 0 in fixed depth, and here the difference being between a particular buffer or a margin, as I showed earlier. Then we used a video lectures dataset which had about 18,000 users, and here I've only put the results from the main dataset or the big dataset. And here what we can see is that the novelty model does really well in recall, which also leads to better F1 score. Here you can see that there's a dominance of the naive persistence and naive majority models, but then at the same time, if you think about these models as a recommendation system, if you use the previous action as the next prediction, we will not be able to rank materials in a corpus. So instead, these algorithms provide probability values where you can rank materials to actually provide recommendations. And then we further analyzed the differences between how TrueLearn models are getting better results compared to the knowledge tracing models that are also doing a similar representation. And we could see that the TrueLearn models are far better at predicting when the topics are fresh. So here the topic sparsity, as you can see, is the number of unique Wikipedia concepts that are encountered in a user session divided by the number of events. So if the unique number of topics are big, what that means is the diversity of new topics that appear in that person's session is larger. And here what you can see is in the knowledge tracing model, when the topic sparsity, which is the when the diversity of topics increases, the performance suffers from it. And here you can see from the TrueLearn models actually perform better when the topic sparsity is high. And one interesting thing here is if you look at the scale of the the x-axis, in knowledge tracing it ends from topic sparsity 4. If it is greater than 4, the F1 is 0, whereas in the knowledge tracing one you can go up to around 5 topic sparsity while still retaining good F1 performance. So in this paper, from the experiments that we ran, we identified a few interesting conclusions. So one of them is educational recommenders demand for additional features that go beyond a conventional recommendation system, which I also argued earlier why that is the case. And we also saw that entity linking provides a good scalable and domain agnostic content representation, which also preserves predictive performance at the same time. So we've managed to automate the expert labeling aspect of this problem and also do it in a way that it can be scalable because it's automatic, and it's domain agnostic because Wikipedia captures a lot of knowledge that belongs to a lot of different subjects. At the same time, we've shown that we can retain performance, and then we've also shown that TrueLearn performs significantly better with unseen topics compared to knowledge tracing counterparts, and these are all Bayesian models that perform really well with very little amount of data. And here the other interesting thing about these models is these models don't share information between users. So for the individual user, the only information from that individual user is being used to model the learner representation. Therefore, the privacy issues are minimal. At the same time, we don't have to rely, we can compute these models parallelly for all the learners simultaneously. And if you look at the code, it's also implemented in Spark, where all the learner representations are parallelly computed. If you have a cluster, you can scale it very easily. So from this we want to go to a few future directions. One of the things is we want to have semantic TrueLearn. So far, although we use Wikipedia topics, we are not exploiting the relationships between these topics. And what we want to do next is to exploit the relatedness between these topics to identify sensible learning directions for a learner, and also use knowledge about the seen topics and their relatedness to a freshly unobserved topic that comes up in a future event. And then we want to build the other parts of this learner model. So the green part is the middle part, as you saw earlier. So the other components are should be added to this whole engagement picture, and we want to build the whole graphical model for the user engagement that incorporates quality, knowledge, novelty, and interests. And eventually finally what we want to do is to integrate this algorithm with the TrueLearn X5 Learn learning platform, which is another output from the X5 Gone project. So I mean, it's already online. You guys can go discover educational materials in there. So what we want to do is, currently we have this platform where users can register, they can search for videos, PDFs, they can watch these PDFs or videos. What we want to do is to now incorporate TrueLearn to provide recommendations to these users.